Welcome, friends of freedom.
The public domain SID might seem somewhat inconspicuous, just one sound chip, replica among many, but sometimes it is the small, inconspicuous things that trigger something great. I would like to tell you about this inconspicuous public domain SID today. It all started in 2020 with the free Stereo SID, a hardware platform for software developers who could use it to program their own SID. The free Stereo SID still used the rather simple approach of playing waveforms with a waveform pointer. Despite this primitive method, and being far removed from the phase counter principle of the real SID, the sound sounded quite good, but not precise enough to accurately replicate all the sounds of the SID. A short time later, it continued with the USID 64. With the USID 64, work began on generating sound using a 24-bit register. Over the years, small improvements were made repeatedly, but unmistakable incompatibilities remained. That only changed a few years later. In the meantime, a successor using the new Raspberry Pico had already been planned in 2022, and the corresponding circuit board was developed and manufactured, but ultimately postponed due to other projects. In 2025, the Public Domain SID project was brought to life, intended to finally fix all the problems of its predecessors. The main reason for resuming development on a new replica was the new U2600+8 Fantasy console, which contains two sound chip sockets as well as the old VCS 2600 chips from the year 1977, namely the TIA graphics chip, the 6507 microprocessor, and the 6532 controller from MOS Technologies. This new console will play a major role in the future. Work on the public domain SID took about an intensive 5 months, with approximately 1 month spent on research to understand the exact operation of the Commodore sound chip in detail. During this time, comments by Bob Yance were studied, as well as bugs found in the sound chip that had to be taken into account. Everything is built on the 24-bit phase counter. This is the heart of the Commodore sound chip. It is a quite simple principle. The phase counter is a counter that adds a predetermined 16-bit number which can take values from 0 to 65,535 at every clock cycle. Depending on how large this 16-bit number from the frequency registers is, the counting speed accelerates. The upper 12 bits of the phase counter, bits 23 to 12, then generate the waveform. This means oscillations per second. If the frequency registers are written with a high 16-bit number, the phase counter counts correspondingly faster, more oscillations per second are generated, and the resulting tone sounds higher. The highest bit of the phase counter, the most significant bit, abbreviated MSB, plays a special role here. With a triangle waveform, this bit determines whether the waveform value rises or falls. That was it already. That is the simple principle of how the SID internally generates its waveform and makes tones audible. So, no rocket science, on the contrary, very simple. In addition to the waveform, the sound chip generates an envelope curve, which influences the volume of the generated waveform. This envelope rises from 0 at a certain speed, holds its value for a certain time, and then falls back towards 0 at a certain speed. The envelope, like the frequency of the waveform, is controlled via registers. A bug in the SID, the so-called envelope bug, occasionally causes the envelope not to start with the value 0, but with the current envelope value. Therefore, in practice, a hard restart is performed to bypass the problem, which in turn brings further problems with it. Let's come to the last element of the sound chip, the filter. The filter is a state variable filter and also not witchcraft. There are very good explanations and formulas on the internet regarding how this filter works and is used. To save computing time, most replicas use fixed point calculations for the filter, which ultimately sounds a bit less precise. In the public domain SID, however, floating point calculations are mainly performed. Fixed point calculations are only resorted to for digisamples, as the digisamples sound cleaner that way. In a direct comparison, the difference is more than clearly audible.
I'm gonna wreck it! I'm gonna wreck it!
This is also one of the reasons why digisamples sound a bit worse on the original SID than on a replica. The main challenge in designing the filter is finding an optimal curve for the cutoff frequency and resonance. These two curves determine how close the replica comes to the original. This is among the most laborious work on a replica, as countless games and music must be tested and compared to ensure that no boundaries are crossed here and authenticity is not lost. Let's move on to the hardware. During the development of the public domain SID, one of the biggest hurdles was programming the microprocessor, the RP2350, the successor to the RP2040. Unfortunately, the first version was burdened with some errors, which delayed software development. To achieve perfect timing in interaction with the computer bus in connection with the sound chip, reliance was placed on the PIO programming of the RP2350. These are small programs that take control of the individual pins. For this purpose, a dedicated PIO assembler was programmed, and each assembler program was brought to perfection for its respective task over weeks of work. Thus, not only could the paddle control be fully automated and independent of the microprocessor, but also the data bus transfer between the computer and the sound chip. With this basic framework, we moved on to fine-tuning and very intensive listening tests. The SID comparison board was a very big help here. This board can be equipped with multiple sound chips, and with a small switch, the audio output of each sound chip can be switched separately in real time. Without this very useful circuit board, fine-tuning would not have been so easily possible, because only in this way can one quickly switch during certain passages and check whether a previously existing problem has been satisfactorily solved. For the listening tests, certain games and music tunes were then used for assistance, such as Wizard of War, Alien, Fix-It Felix, and many other games. Certain games read specific registers in real time and write to other registers with this data or require specific data exactly cycle accurate. This is very time critical and leads to errors in the sound if handled incorrectly. Here are some examples. Another problem is samples that are played via the chip. There are different possibilities to feed the SID registers with them. All of this had to be taken into account as well. Ultimately, a great end result came out of it. When development was as good as finished, but various listening tests were still being conducted, it occasionally happened that, assuming the original SID was currently being listened to, one intended to switch to the Public Domain SID, but it was already activated. That makes it more than clear how close the Public Domain SID is to the original. This marks a milestone, not only because of the very successful sound, but above all because it is the first public domain SID ever. We have now reached the end. It only remains for me to wish you lots of fun with the Public Domain SID.